Graphing the exponential models. You've been introduced to 4 exponential models now. You've seen the exponential growth model, and example 1 has an exponential growth model in it. You've seen the exponential decay model, and there is one in example 2. You've seen the learning curve, and there's one of those in example 3. And finally, example 4 has an example of a logistic growth function. What we want to do is take a look at how we can graph all these on the calculator. The first two are pretty straightforward. The second two have some features that are useful for us to find using a graph. Why would you want to graph these? Well, as in examples 3 and 4, the learning curve and logistic growth curve, there's certain features that you can find more easily if you look at them visually. However, for all of them, putting them into the calculator makes it easy, one, to evaluate them, whether just from the regular kind of calculation screen or from the graphing screen. You can also set up a table to work with them. So it gives you lots of different options for working with these functions and learning about them and finding out the bits and pieces of information you need to know specifically about them in different problem situations. So let's take a look at example 1. We're going to graph q of t is equal to 60e to the 0.12 times t. And I'll remind you that the calculator only works with y's and x's. So q of t is going to be the equivalent to y, and t we're going to have to replace with x in the calculator. So if we go to the y equals menu, we're already given y equals, so we don't have to worry about that. We just have to worry about what's on the right hand side of the equal sign. So we're going to type in 60, and then we're going to press the second key and the ln key. We see above the ln key in the same color as your second key, e to the x. So we get e to the, and then we open a parenthesis. We can type in our entire power here. I'm going to type in 0.12x. And you don't have to have the 0 before the decimal. Kind of a style issue as to whether you put that in or not. But any zeros that you have after the decimal, that is to the right of the decimal place, you have to be careful of those and make sure you get them. Alright, put in the parenthesis, and we enter that, and there is our logistic growth function. Now what we're going to do to graph this is we're going to start with the window. We're not just going to go to a standard window. And part of the reason for this is that if we just examine this, we see that 60 is the initial value, and we know this is a growth function, so it's going to get larger as x gets larger and as we move away from that initial value. So if we do a standard window, which is what you see right here in the window screen, we're not going to see any part of the graph because it starts at 60 and goes up. There is no part of the graph between negative 10 and positive 10 for the y, at least not in the positive or non-negative parts of the x-axis. And usually that's what we're looking at, is values of t or values of x that are non-negative. So what we're going to do is we're going to change x-min and x-max. And I'm going to choose to use 0 for x-min. And let's say that we use 25 for x-max. Sometimes your problem will give you a domain for a function, and you can use those specific domain values for x-min and x-max. Sometimes you just kind of have to guess. I'm going to leave x scale at 1. 25 tick marks isn't too many to have along the x-axis. I'm not going to choose anything for y-min, y-max, or y-scale at this time. What I'm going to do is I'm going to use a function in the calculator called zoom_fit. And what zoom_fit does is it takes a look at your x-min and your x-max, and it takes a look at lots of different values in between, and then it figures out in that range of values where the smallest value is for y and where the largest value is for y, and it uses those for y-min and y-max. So it fits the vertical part of the calculator to fit the graph very nicely. So I'm going to press zoom, and you can either cursor all the way down until you find zoom_fit, it's option 0, or we can just press 0, and to save time I'm just going to click on 0. The calculator will work for a few minutes trying to figure out what y-min and y-max are. Once it knows what they are, it'll set them, and then it'll actually go about drawing the graph. So now that you see the graph coming up, that means the calculator knows what a good y-min and a good y-max are, and it's going to start graphing. You'll notice on the left hand side we have what looks like a thick y-axis. And what that's really telling us is that the tick marks are so close together that you can't distinguish in between them. So we're probably going to have to go back and at least change y scale on our graph. Another thing you'll notice is that all we have are dots on the bottom part of the calculator where the x-axis might normally be. And that tells us that we are above the x-axis somewhere and is just showing us some tick marks so that we can look at. So to get maybe a slightly better picture, let's go and press our window key and let's move down to y min. Let's set y min to 0 so we can see from 0 all the way up to that y max value. And you'll see that y max is 1205. So between 0 and 1205, the calculator is going to try to put 1205 tick marks if we leave y scale at 1. And that's just way too many. So let's maybe set tick marks to be 100 units apart on the calculator. So we'll just change those two things and we'll graph again. And now we'll have both axes. We'll have the x-axis and the y-axis. We still have a good y max in here, so we can see the entire graph as it exists between x equal to 0 and x equal to 25. And we have better tick marks on the y-axis now. As we look at the graph itself, we see that it definitely looks like an exponential growth graph. It starts off growing kind of slowly as we have smaller x values, and as x values get large, the steepness of the curve, if you imagine to walk on the curve from left to right, gets steeper and steeper. That means that the values on the curve are growing faster and faster, what we usually refer to as exponential growth, since this is an exponential growth model. All right, from here you can press the trace key and trace on the graph. You can pick specific values to evaluate at. Since you're in the y equals menu, you can also use the table. You have lots of different options for evaluating and working with this function here. If you need to deal with it for negative values of x or for values of x greater than 25, you'll have to adjust the window, and you can go through a similar process as the one we just finished to make sure that you get a good picture of the graph. If you were asked to draw a picture of this graph on paper, to sketch a graph maybe, you could use this as a guide, and you could also find a couple of values, specific values, pick some x's between 0 and 25, enter them in once you're in the trace mode, take the y values, plot those points, and then draw a nice smooth curve through those points that looks about like this. So lots of different options become available to us and are pretty easy to do once we have the function in the calculator. All right, let's take a look at example 2, and here we have an exponential decay model. Let's go into the y equals menu. Let's clear out example 1, and we'll type in example 2. So again, q of t is the same thing as y. So it's going to be equal to 200. And to get e to a power, again, we press second and the ln key, since we see e to the x above the ln key in the same color as the second key. And in this case, we have negative 0.045t, and we're going to replace the t with x in the calculator. So negative 0.045 and x, and then we'll close the parenthesis and press enter so that we have that entered into the calculator here. All right, same idea as before. We can choose a minimum value and a maximum value for x first. 0 and 25 are probably just as good now as they were in the previous example. We'll let the calculator choose y min and y max. So I'm going to press zoom, and I'm going to choose option 0, zoom fit, which tells the calculator to pick its own y min and y max. Again, based on the x min and the x max that we've chosen. So the calculator is thinking about that, and now it's starting to draw. While it's drawing, I'll point out one or two things. Once again, we see the tick marks without an axis at the bottom of the screen. That means that we are starting above y equal to 0. So we'll probably want to adjust that once we're done. And you'll also notice on the y-axis itself, there's a long distance in between tick marks, which means that the previous tick mark size is probably too big, and we'll want to make it a little smaller. So here's a picture, and this definitely looks like an exponential decay function as we see it decreasing from left to right, and it gets less steep as we move from left to right. Let's make those changes to our window that we were just discussing. So we're going to go down and let let y min be 0. So we'll enter that in. And y min to y max is a total of 200 units. So we could probably let our tick size be as small as 10. That would give us 20 tick marks on this axis between 0 and 20. I'll press enter to keep that, and then we'll press graph to regraph the picture with those changes. And it's going to be roughly the same picture. We're still going to see the decrease from left to right. It's going to get kind of more shallow or less steep as we move from left to right, as exponential decay functions do. It's just going to be in a picture now where we have both axes and a better choice of tick marks. So that's a pretty nice picture. Now that this is in the calculator, again, you can evaluate at any point from 0 to 25 for t as the original variable in the problem. You can use the table. You can use this to help you sketch. There are lots of things that you can use the calculator to aid you with if this was part of a larger problem. All right, let's move on to examples 3 and 4. These curves are a little bit more complex, if you will. There's a little bit more the calculator can do for us and explain to us as we go along. So let's see what we've got here. I'm going to go to the y equals menu, and I'm going to clear out what we had before. And we're going to look at this as being y is equal to 100 minus 35 e to the negative 0.97x in the calculator. So I'm going to enter that in. 100 minus 35 and then we're going to do e to the missed it there, negative 0.097x. And then we'll close the parenthesis and press enter to store that in the calculator. All right, now I'm going to once again go to the window, and we'll choose an x min, x max, and x scale, and then we'll zoom to fit. Let's keep 0 and 25. Those have worked well for us so far. So then we're going to press zoom and press 0. The calculator is going to go through, try to figure out what a good y min and y max are, and then we'll graph the function in the resulting window. So here's the graph. We see very few tick marks on the left, so we're probably going to need to adjust our spacing there, y scale. And we also see that we're getting just tick marks, no axis in the bottom, which means we're probably going to need to set y min to 0 so that we can see both axes. We look at the shape of the graph, and we're definitely getting a learning curve here. We see that it is increasing quickly on the left. If we were walking up to the left-hand side, that would feel like a pretty steep hill, but the hill gets less steep as we move along. As a matter of fact, it looks like kind of like if we kept going off the screen, we might approach the top of the hill. All right, let's adjust our window first, and then we'll see if we can't figure out a little bit more about that hill. So what I'm going to do is I'm going to take y min and set it to 0. I'm going to leave y max alone, and I'm going to leave x scale alone. I think 10 is fine there. We're now going to have about 10 tick marks versus just the 3 or so that we had before. And that should give us the ability to read the graph roughly pretty well. So just changing y min to 0, I'll now graph in our new window. We can see that the function actually starts well up the y-axis relative to where it finishes on the right-hand side of the axis. And what you'll notice, if you were paying attention to the window there, the y min was 65. That's the initial value, the value of the function when t is 0. And we get that really just from subtracting 35 from 100, that's 65. If you plug 0 in for t, t times 0, times any number is 0, and any number to the 0 power is 1. So e to the negative 0.097 times 0 is just 1. That leaves us with 100 minus 35, or 65. All right, and then from there we grow, but the growth slows down. Let's see if we can't figure out roughly kind of what a maximum value is for this hill. There isn't really a true maximum. There's kind of what we might call a theoretical maximum. The function will never quite reach its potential maximum value, but it will get arbitrarily close to a value. It's one of the features of the learning curve. So what I'm going to do is I'm going to take the window and I'm going to extend those x values out a little bit. I'm going to go to say let's double it, and let's go x from 0 to 50. I'm going to change my x scale to 5. I don't want 50 tick marks. That's a lot for the calculator. I'm going to leave y min at 0. But I'm going to change y max. Since I'm letting x go out further, I need to let y go up further as well, because we know that function is going to continue to grow. Exactly how much? It's not necessarily easy to say. I'm going to guess 120 should be more than enough. And I'm guessing that because the original window we had y min at 65, y max at about 96, or a growth of about 30 in the y direction for 25 x's. I'm going to go 25 more x's, but we know the growth is going to slow down, so I'm giving it about room for about 25 more growth in the y direction, and that should be enough room. If not, we can always adjust. I'm going to leave the y scale at 10, and I will graph. And what you'll see as the graph is drawn here on the calculator screen is that it gets more shallow and more shallow. It starts to look flatter and flatter and flatter all the time. It takes a longer and longer distance for it to kind of go up or grow at all. And what we're going to do here is we're going to, once the graph is done, go into the trace mode. So go ahead and press the trace key. And then we're going to kind of pick some values along the way. We're going to start with x25 just because that's what the calculator gives us as a default, and y is about 97. Now let's increase that to maybe x35. So let's type in 35 and press enter. And now x is up to about 98.8 or almost 99. If we go to 45 and press enter, we're up to about 99 and a half, 99.6 if we rounded. If we go to the edge, we can type in 50 and press enter, and we're up to 99.7. So we're still growing here. We're not really seeing that we're getting to a specific value. We are still seeing growth here. To keep going, what we probably should do is take our window, extend it out even further, like maybe to 75 or even 100, and then graph further. Probably wouldn't need to adjust the y min or the y max, just the x max. And then using the trace mode, continue to see what you see. If you do that, and I'm going to leave that up to you as to whether you do that or not, what you should find is that the values are getting closer and closer to 100. And at some point they will be 100 because the calculator will just round to that. Technically they never get there if we had enough decimal places to show that. We would always be a little under 100. And you'll notice that the first number in the learning curve is exactly 100. And if you read the textbook and think a little bit about what happens when t gets very large, this expression e to the negative 0.097t, which is really the same thing as 1 over e to the positive 0.097t. The bottom part of that fraction, if you think of it as a fraction, is going to get bigger and bigger and bigger as x gets bigger. And 1 divided by ever bigger numbers always ends up being a smaller number, as in 1/2, 1 divided by 3, 1 divided by 4, 1 divided by 5. The actual value gets smaller. So that expression, e to the negative 0.097t, as t gets really large, starts to look more and more like 0. So we end up starting to look at things like 100 minus numbers that get closer and closer and closer to 0. And eventually it starts to just look like 100. So that's the maximum value. All right. Example 4 is our last example here, our logistic growth function. Let's go back into our y equals menu. Let's clear out our function. And let's enter this. Let's type in 105 divided by, and then we're going to have to put the denominator in parentheses because we have other things going on in it. We want to enforce order of operations. So we're going to have 1 plus 34, and we're going to have e to the, and I just accidentally got 10 to this, so I'm going to go back and delete that and try again. We're going to use e to the, and in this case the power is negative 0.17, and again we will use x in place of t on the calculator. Close the parenthesis, press enter. Alright, now let's choose a window here. I'm going to let the x part of the window go back to 0 to 25. I'm going to leave the x scale at 5. That's probably okay for what we're doing here. And I'm going to zoom fit. Ask the calculator to find a good y min and a good y max. So we'll let the calculator think about that for a moment for this function, and we'll see what kind of a picture that we end up getting for it. Again, from x equal to 0 to x equal to 25. Alright, and this is logistic growth curves are kind of our S-shaped curves. They look like an S that's kind of been slanted. They tend to grow fairly quickly in the middle, and they tend to grow somewhat slowly on both ends, both at the left side and the right side. Alright, and we see this one growing slowly on the left, then starting to pick up speed, and then it's kind of leveled off, and we see it just kind of going off the screen there. Almost looks like it's a linear function at that point. And we're not really getting that S picture, so let's extend our x values out. Let's maybe let x max be 50. And we'll enter. And let's zoom fit again. So we're going to press zoom and 0. And the calculator will recalculate. Again, yours much faster than my computer version. And then the calculator will start to draw a picture. And let's see if we get a little bit more of an S shape this time. That's what we're looking for when we see a curve of this form, this logistic growth curve. We want to see that S shape. We kind of want to see where it starts, how it starts to grow more quickly, and then how it eventually starts to slow down. And it'll taper off like that learning curve did. It'll actually start to head toward some single value that's kind of a theoretical maximum for it. And in this picture, we can actually see that happening here. All right. So we don't have the x-axis, so let's make another minor adjustment to our window. We'll regraph one more time, and then let's talk about the picture we have. Y min in this case is 3, and I want to set that down to 0 just so I can see that x-axis and get a little bit of a better relative feel for everything. So I'm going to set y min to 0. I'm going to press enter, and I'm going to regraph the function in the same window. Alright, you'll notice that the y min that we had there was 3. That means that when x is 0 in the calculator, y is 3, or in their example, when t is 0, q is 3. And we get that from 105 divided by 35. And 35 comes from 1 plus 34. Again, if you set t equal to 0, that expression e to the negative 0.17 times 0 will just become 1. And there we get our initial value. Now this also has a maximum value, and let's see if we can't get kind of close out there and maybe get a feel for what it might look like. I'm going to press trace, and I'm going to start out around, let's say 40. We can see right here at the beginning for 25, but that's kind of in the middle of the growth. So if I let x be 40, I see that y is about 101. If I now let x be 45, I see that we grow from 101 to 103. And if I let x be 50, I see that we go from 103 to 104. We're definitely slowing down. And if you look at the problem here, there's this number 105 in the top that's just a little bit above 104 here. And it turns out that 105 is our theoretical maximum. Again, using the same argument as we did before, e to the negative 0.17 times t, where t is allowed to get really large, that expression starts to look more and more like 0 as t gets bigger and bigger, which means 34 times that expression starts to look more and more like 0 as t gets larger and larger, which means the whole bottom here starts to look more like 1 plus 0 or just 1. So we take 105 and divide it by numbers a little bit bigger than 1, but getting closer and closer to 1 as t gets larger and larger. and it turns out we can't get any higher than 105. Matter of fact, we can't technically ever get exactly to 105, even though if you do extend the graph out again, say take x to 75 or 100, and repeat with the trace key, you will eventually get values of x for which the calculator tells you y is exactly 105. But the calculator is rounding when it does that because it doesn't have the capability of showing you enough decimal places. I hope this video gives you a good idea how to use the zoom fit option for graphing, number one. And number two, you'll remember a little bit about the shapes of these exponential model graphs and some of the things that we can use the calculator to help us learn about those exponential models.